Okay, so this is a bit of a survey, a very brief history of identification theory in the quantum setting. So as everybody here should be aware, identification theory is something that originated here in Bielefeld. It's one of the proudest inventions, I guess, of Rudolf Ahlswede. And so it was natural that when Peter Löber and I started as PhD students here in the late 90s, we would consider this. And in fact, Peter Löber wrote, who's sitting there in the back, wrote a PhD thesis on the subject, which was really the beginning of quantum channels in identification theory. We put this talk in this session because of the early understood relation between identification and common randomness theory that Imre Cisa mentioned already briefly. So this theory in the quantum case is unfortunately very small still after 10 years. So the only authors or co-authors that published on this are Peter Löber, Rudolf Ahlswede, and Patrick Hayden recently. So here is a brief outline. I want to start with a classical case, classical channels, then go into quantum channels. This is basically Löber's theory here, and something that I did then shortly afterwards with Rudolf Ahlswede. And then I want to go to something that looks a bit weird at first, but it actually will bring us back to classical identification, which is something we call quantum identification, where the information to be identified is actually quantum state. So this is something that probably most of you know. So I prefer to draw little pictures instead of writing formulas. If you know information theory, you know how to translate this into the corresponding definitions using epsilons and deltas. So in the classical theory, we have a noisy channel. We want to use it asymptotically many times to encode messages. So let me put some symbols here. So the encoding is a probabilistic encoding in identification. So each message is identified with some distribution over the inputs that goes through the channel. And then there is instead of a decoder, there is a decision rule for every alternative message M prime that is whose task is to determine if M is equal to M prime or not with high reliability. And okay, so the celebrated result of Ahlswede and Duke, of course, is that the number of messages you can identify in this way grows double exponential thanks to this hashing that was mentioned a few times before. So you can introduce an identification capacity that is simply the double exponential rate. And in the simplest possible model, when you have just a communication channel with no additional resources, the identification capacity is equal to the communication capacity. So this is kind of just the warm-up. So obviously what you can always do if you have a new channel model, you can try to understand your old theory with a new channel. So we just substitute a noisy quantum channel for the classical channel. Everything else stays the same so far. So we still have messages and so on in the same way. So for those of you who don't know the formalism, by quantum channel we simply mean a linear map that takes density matrices to density matrices. So these are the generalizations of distributions. This map has to be completely positive and trace preserving. So these are technical conditions. For the understanding of the talk, it's not important to understand what these are. These are simply the matrix analogs of stochastic map. Okay, so we want to use the channel again L times. So that's the L's power here. We have the input message, that encodes each message into now a general mixed state. So that's kind of the distribution that we had before. That goes through the channel. It produces some output state, and we have a decision rule that is now a quantum measurement. For each alternative message M prime, we have a binary measurement that should tell us if M prime is equal to M or not with high reliability. So this measurement is simply given by a single operator between 0 and 1. In practice, it's a projection, a good old-fashioned projective measurement in quantum mechanics. So again, it's very clear that based on the previous insight, the number of messages we can have here grows double exponential, and we would like to know what's the identification capacity here. So I don't write a formula because this is actually still an open problem, so I'm just reporting here on progress towards understanding this number. So maybe this is already the first thing you should take away. In the classical case, I think Rudolf Ahlswede and Gunter Dücker, they were slightly disappointed to find in the simple model, without feedback, without anything, that the identification capacity, this new capacity, is simply the old capacity. So it was not. I mean, I think they would have been much happier if it would have been a new number, because that's kind of, that's a true revolution. Everybody can see it if it's a new number. Well, in the quantum case, this is what we will find. It is actually not simply equal to the communication capacity, and even that took us a while to understand. So first of all, using this common randomness insight, we can clearly see that the identification capacity is larger or equal than the communication capacity, because we can always use the channel to communicate, hence to establish common randomness, and then to use a little bit of zero-rate communication to do the identification part. So unfortunately, we don't really have a usable formula for this communication capacity. We have there is some sort of progress in quantum information theory that relates this number to this so-called Holevo capacity, which is a maximum quantum mutual information analogous to Shannon's formula. So I wrote out the formula here just so that you have it. Unfortunately, it is known by now, thanks to Hastings from a couple of years ago, that this number is not additive, as was conjectured for several years. And so the operational capacity in terms of maximum rate of communication is actually larger than this number, and it's equal to the regularization. It's equal to this limit of 1 over L chi of n to the power L. Okay, so that's in some cases we know that C is equal to chi, but in general it's not. So in any case, this is just large or equal. What else can we say? So I'm starting with history now. So as I said, Peter Löber in his PhD thesis made an important observation in my view, which is classically, we don't just want to. It is possible not just to ask about a single question, a single message at the receiver. You can in fact ask all these questions simultaneously, and each of these questions will receive individually the correct answer with high probability. Of course, over the board, across the board of all messages, you will make a lot of mistakes. But if you just look at a few of them, that's fine. Now, quantum mechanically, that's not a given, the way I define this problem, because I just introduced for each message m prime another measurement, and they might not be compatible. They might in fact be complementary observables. So if you ask in addition that these measurements do have a simultaneous implementation, so this is what Löber called the simultaneous ID capacity, then you get a potentially different number, and for this number he could show that it's actually equal to the communication capacity. So it's kind of, back to Ahlswede Dück, that identification capacity is equal to communication capacity. And I'm very careful here. I'm writing here also a thing about a technical condition, which at first, I think both of us, Peter and I, we thought of it as rather tame. But as you will see, also this other technical condition comes into showing that without this simultaneous assumption, these numbers are different. So a particular case when this technical condition is satisfied is when all the encodings are separable. So these non-entangled states across the L uses of the channel, which is, to be fair, is a valid and maybe reasonable assumption. In that case, the treatment of Peter as a corollary actually gives that this. So this is now the simultaneous ID capacity with separable encodings is equal to the communication capacity with separable encodings, which we know is equal to this Holevo chi. So this is kind of a Shannon theoretical formula. And we have a strong converse, which was kind of a thing that also we were quite keen on having. So all this here kind of goes back to certain ideas that were laid out by Hahn and Verdoux in two papers in 92 and 93. So that's kind of stage one. So unfortunately, Peter decided not to continue this direction of research. I was left here in Bielefeld with Rudolf Ahlswede, and we decided to look a little bit what happens if you give up this simultaneity condition. And the simplest channel you can look at are so-called CQ channels. So they have only partial quantum character. Their inputs are essentially classical. You have a finite list of inputs x, and for each input x, the channel will prepare a proper quantum state, a genuine quantum state, rho sub x, on the output. So for these particular simple channels, we know that the communication capacity is equal to this Holevokai, so it's an instance of additivity. And using some new machinery, we could prove that, in fact, we could even prove a strong converse for CID equal to C. So that was published a couple of years after Löber's PhD thesis. And I think to this day, this paper remains one of my proudest achievements. And I mean, the result itself might remain obscure because, as you see, that not many people so far have been shown an interest in quantum identification theory. However, the technique that we introduced there is basically a large deviation version for sums of random matrices. We proved tail bounds of the type of Höfting or Azuma's inequality for random matrices. And that thing apparently hadn't existed before. And it turned out to be crucial for a lot of things that we did subsequently in quantum information theory and in other subjects. So I think, I mean, okay, so apart from the fact that I'm a co-author, I think this most likely is the most important contribution of Rudolf Ahlswede to quantum information theory, this technical lemma that we proved in the appendix of this paper. Okay, here that's the shock. A couple of years later, I showed that in general, communication capacity is strictly less than the identification capacity. And the example is the simplest possible quantum channel you can imagine. It's a noiseless one. It's simply the ideal qubit channel. Simply it takes the state of a two-dimensional system and outputs it without any noise. So it turns out that the communication capacity, and by the way, I didn't write this, the common randomness capacity of such a system is 1. It's very easy to show that. However, the identification capacity is 2. And somehow the reason for that is that you have even more space in the space of mixed states than in the space of the, probability distribution. So it not just goes double exponential, but there is this extra 2 there. So I don't show you any proofs here, as you can imagine. So the idea of this is you find 2 to the 2 to the 2L pairwise almost mutually orthogonal states, mixed states, in fact highly mixed states in L qubits, so in a 2 to the L dimensional Hilbert space, which you can do by random selection essentially, suitably chosen random selection. Interestingly, already a few years before, some of our colleagues in quantum computation complexity, they looked at this problem when you encode with pure states. And there it's quite easy to see that the maximum number is 2 to the 2 to the L. So somehow the scaling is the right one. It's equal. If you only look at pure state encodings, you get this idea that capacity is 1. By mixed states, you double again your possibilities. So from that moment on, we had a real problem. What is the ID capacity? Because it is clearly different. And why is it 2? What does that mean? In fact, you can have so somebody like Charlie Bennett might have an easy guess, because we know some examples where a quantum channel actually might have twice the capacity than expected. But that requires the presence of entanglement, and it's not clear where the entanglement is here. In fact, the issue of what entanglement does to you in this setting of identification remains also open. We have some partial results, but I won't start getting into them. So that was kind of the state of the art in 2004. I think I even wrote a second paper that I don't know where it appeared, where I tried to develop these ideas a little bit further, but basically the only channel that we understood was the ideal channel. So it required changing tracks. In fact, you will see that looking at this even more obscure problem of quantum identification, it eventually also says something about the original problem. So this was something that I remember I was discussing even during our days of PhD with Peter Löber here, with Rudolf Ahlswede. how can we actually quantize the task, not the model, but the actual problem. The actual question itself should also have a quantum version. Just like for each quantum channel, we also can ask about the problem of transmitting quantum states, understood as quantum information, and what's the largest rate of qubits we can encode and decode, which is a completely different question from the classical capacity. So we came up with the following, and I wrote it up in the same paper in 2004. So now we still have the same channel. Our information now is a quantum state. So Alice, the sender, has a pure state. I mean, she gets it simply from someone as the message. And Bob also has a pure state, but I write it in inverted commas here to indicate that he actually has a literal description of what the state is, if you want a list of all the amplitudes in the expansion of some Hilbert spaces. Okay, so let's put this stuff here. So the encoding is just like the channel, a completely positive and trace-preserving map. I mean, it has to be a stochastic map that is physically allowed. After the channel, we get some state that depends, of course, on psi here. Psi is from some Hilbert space. So instead of being a message from a list, it's just a state, a pure state, I have to stress, in some Hilbert space that I call M to remind you these are the messages. So the dimension of M will be important. And for each state phi that Bob has, he must be able to construct a binary measurement, so again, just an observable between 0 and 1, that reproduces in its statistics as if he had measured this guy here on the input state. So the condition is that the probability of saying yes, the trace sigma psi times d sub phi is almost equal to the inner product of phi and psi squared. So this reduces to classical identification if we restrict to an orthogonal basis, because then these guys here can be only 0 or 1. But for quantum states, I also have to deal with all the things in between simultaneously. Okay, so first observation is the dimension now doesn't go double exponential, but only single exponential. So, okay, I think Rudolf Ahlswede was a little bit disappointed about that, but there's a very simple explanation about this. It's because of this Burman et al. Fingerprinting, this pure state construction that I showed before, which we can plug into here, and that adds another exponential. And from the same argument, we see that the quantum ID capacity, so the largest dimension here, basically, or the rate of the largest dimension is less than or equal to the classical ID capacity, because we can just concatenate these two things. And of course, it's also larger than or equal than the quantum capacity of the channel. So if you, quantum capacity meaning that here, instead of a measurement, you have another map that decodes, that does the error correction, and that reconstructs psi. Okay, so in fact, the previous result about the classical ID capacity was a corollary of this stronger result. What I proved back then is that the quantum ID capacity of a noiseless qubit is 2. So you can somehow squeeze 2 L qubits into L by making them super mixed, and you can still do a measurement that somehow does this identification trick for quantum states. But okay, again, this is done randomly. Essentially, you apply a random unitary and throw away half the qubits, and with high probability, you can show this works. So, as I said, we were stuck for a number of years. I mean, there was some kind of feeling that this might have to do with entanglement-assisted capacity, because it was the only instance where we knew this difference between 1 and 2. It required a new impulse from my colleague Patrick Hayden, and also a new type of insight, which we worked out eventually in this paper that I had the honor eventually to dedicate to the memory of Rudolf Ahlswede. That will appear very soon in the IEEE transactions, because I think it really, I mean, you can see I took this upon me after Peter Löber left, after Rudolf Ahlswede was also not so interested in the quantum theory. Somehow, for the last 10 years, I've been doing the quantum identification theory. So I think I mean, also personally, it's a bit of it's a pleasant culmination of a lot of efforts. So one thing that we understood, thanks to insights of Patrick's, is that this quantum ID capacity, it can be larger than the quantum capacity, for example, for the noiseless qubit, 1 versus 2, but the condition of vanishing is the same. So QID is equal to 0 if and only if the quantum capacity is 0. So you need to be able to transmit without, in other words, to identify, which is kind of, you know, what we know from the classical analog. And here are some formulas. So this looks really horrible, maybe, but since I have a couple of minutes, maybe I use the time to explain this. So the formula is as often in quantum information theory, and in fact, just as the formula for the quantum capacity, we only know how to express it as a regularization limit of quantities that are information theoretical. So this is kind of one step removed from the definition, because we don't use epsilons and deltas anymore. So it's this limit of many uses of the channel of this Q superscript 1. And Q superscript 1 you might think of, this would be the capacity formula in our dream world if we had single letter formulas, if we had additivity, which we don't in fact in this case. So it's the maximum quantum mutual information over states that can be generated from the channel. So here we tensor the channel with an identity, we apply it to an arbitrary bipartite state, we get some family of two-party states. So as I said, we get the maximum quantum mutual information over such states where the so-called coherent information is strictly positive. So these are the definitions. Coherent information is the entropy of B minus, so that's the output of the channel minus the joint entropy of sigma. And the mutual information is, as you would expect, the sum of the two, entropy of A plus entropy of B minus the joint entropy. So since this didn't look very nice, and since we knew already that a noiseless channel has capacity 2, we came up with this idea, what happens if you can amortize? So let's say you are allowed to borrow a number of noiseless channels. So it's a bit like this idea of having access to extra communication in the common randomness theory, which you of course then later you have to pay for, because you can't just take as much as, you can't just take arbitrary communication, because that would allow you to do anything in this kind of game. So we are allowed to borrow an ideal channel, an ideal qubit, but then we have to amortize it at the proper cost of 2 per qubit, as we know. And then we find that the amortized quantum ID capacity is actually equal to the maximum mutual information over all states, because this extra communication in the amortization, it has kind of the side effect that this condition goes away, which is the whole problem in this regularization. And this number, it was known before. Charlie Bennett and his colleagues, they came up with this capacity formula for the so-called entanglement-assisted classical capacity of a channel. That is a system where you have access to the channel and unlimited entanglement between the unlimited quantum correlation, to be precise, between the sender and the receiver. Okay, so in the last couple of minutes, I just want to show some examples and some implications for the classical ID capacity. So for the CQ channels, clearly it has quantum capacity 0, so also ID capacity, quantum ID capacity 0, but amortized is equal to the classical capacity. For QC channel, this is kind of the opposite. These are input channels that have quantum input by classical output. In other words, it's a measurement, a quantum measurement. Also, of course, the ID capacity is 0, because quantum capacity is 0. However, for rank 1, at least for rank 1 measurements, so if you want for complete measurements, the amortized is again different from 0, equal to the log of the dimension of the measured Hilbert space. In both cases, we can show that a 0 rate of amortization, in fact, a constant amount of amortization does it. So it can have this huge jump with just a little bit extra. And here's an important example: erasure channel, where you see another difference between amortized and non-amortized capacity. So erasure channel is, as usual, with probability Q, the state is simply sent away and replaced by some error symbol. The amortized capacity is this here, twice 1 minus Q. This 2 is always an acknowledgement of the entanglement assistance. The non-amortized looks similar, at least for very low noise. So it's 2 times 1 minus Q if Q is less than half, and from 1/2 to 1, it's 0. And that's again because the quantum capacity is 0 in this regime. And we can also show that in this to achieve this here, we do need non-trivial rates, non-zero rates of amortization for Q larger than 1/2. So it was another problem we had for a while. We didn't know, because we had only these examples of zero amortization rate. So here are some implications for the ID capacity. So obviously we get this lower bound, which on the classical identification capacity of the quantum channel, which of course in practice is not very useful because this is very hard to evaluate or even to bound. However, for very low noise, this tends to be equal to the amortized one. And then it's easy to evaluate. So then we know that it's equal to this entanglement assisted capacity. And so that's a very nice number to calculate. And it's very large too. So obviously this is an improvement for some channels, it's for low noise channels, even though it can be a drastic improvement. For example, previously we only had that is larger equal than the capacity of n. I mean, that was the other good lower bound. Then even this amortized capacity can be a lower bound if we know that the amortization rate is low enough. Like in these examples that I showed before, if the amount of amortization is little o of log L, because then we can use the classical communication to describe the quantum state that we need to send in these very few qubits by classical means with an exponential overhead, but this will be still little o of L, so it's no rate added. And so, for example, this gives us that the ID capacity of the erasure channel for erasure probability less than or equal to 1/2 is equal to 2 times 1 minus q. Previously, we only knew 1 minus q. There is, of course, I didn't show you the upper bound, but this is it's a different kind of accounting and discretization argument that I don't want to go into. And similarly, for these QC channels, this is even more drastic. So these complete measurements, I can show that now we can show that the ID capacity of this thing is log D. So previously, when we look at Peter Löber's PhD thesis and the simultaneous condition, which is a good case to look at because the output here is classical. So all your observations you want to make, they are just classical decision rules. So any ID code automatically is simultaneously. So when we look at his thesis, he says actually this is equal to the communication capacity of this M, which is equal to chi. And in general, unless these my here form an orthogonal measurement, yes, I finish in a moment. Unless they form an orthogonal measurement, this chi is less than log D. And in fact, it can be much less than log D. It can be as small as a constant compared to growing log D. So where does this discrepancy come from? And it bothered me for a while. And eventually, I think I pinned it down to Peter Löber's what I call the technical condition, because in his analysis, and it's very important in the analysis for doing a particular combinatorial counting argument, to restrict to encodings to mixed states, which are mixtures of kind of smallish subsets of pure states. And in this way, you cannot get all the mixed states. You can get, for example, all separable states, but you will not exhaust all the input states that I need for this scheme here. So there's yet another thing going on here that simply has to do with that there are even too many pure states to deal with. It's the fact that the number of pure states discretized grows double exponential instead of single exponential. So, and here are my two favorite open questions. From all we know, it could be that the identification capacity of a noisy channel is equal to the entanglement assisted. I mean, in the sense of the maximum quantum mutual information. I don't know operationally what these two things have in common, because here we need entanglement and there we don't. But that would be very nice to show, because we would finally get a formula for this, even though it would be a bit of a disappointment because it's again something we know already. And second, there is kind of a whole research program similar to the role of classical common randomness in identification theory. We can also ask for what happens if we have a given quantum state, quantum correlation. And I did something in 2004 when sender and receiver share a certain amount of entanglement, but if they share just an arbitrary bipartite state, that's completely wide open. And how this goes together with quantum channels plus entanglement, also we don't know. So these are, I would say, these are the two main directions in this field at the moment. Thank you very much.